Hi, it's time for another math easy solution. Time to discuss further into trigonometric substitution. Now look at example 4, which states find the integral of x divided by square root x squared plus 4 dx. Now this example is useful because you don't actually need to use trig substitution. Basically, since this example, well, it is possible to use to solve it using trig substitution because of this square root x squared plus 4, as I showed in my earlier videos. But sometimes it might be easier to just do regular substitution. But first, I'll do the long way and show you that sometimes trig substitution is harder and you don't actually need to do it. So if we look at trig substitution first. Now if we look at this right here, since we have x squared plus 4, this is basically, you could write it as x squared plus, well, 2 squared. So and we look at this 2 here, and also from the introduction to trig substitution, I showed that if you have a form like this, you could use the trig substitution of x equals 2, well, 2, which is this variable right there, this constant there, 2 times it by tan theta. So if it's x squared plus a number squared, then you would write x times that number times tan theta. Now d of x, or the differential or derivative, would be, well, 2 times secant squared theta d theta, and you can see proof of this in the video link below. The derivative of tan is just secant squared theta. So now that we have this part, and also because tan theta it needs to be a one-to-one function, we have to define this theta as less than pi over 2 and greater than negative pi over 2. And the reason, again, is it has to be a one-to-one function. So in this case, tan looks something like this, and then these are at these points is basically pi over 2 and negative pi over 2. And this is why this is our theta, and that's our tan theta. And since it just keeps repeating itself, it goes like this, etc. So basically we're just selecting this range right here. Yeah, and just so basically each point right here, or each y value only has just one theta value right here. Okay, so now that I've basically recapped why we have to define this here, and now if we get down to this, just plug it in. So we have this x squared plus, well, 2 squared. This just equals 2. Now plug in the x, which is going to be 2 squared, tan theta squared plus 2 squared right there. Now this equals 2. Take the 2's out. If we factor it out, this becomes, well, 2 squared, and then tan squared theta plus 1. And now this right here, if we recall the trig identity, this just equals to secant squared theta right here. Write this better. So that equals that part. Now if we square root this 2 squared, that's just 2. And now we have 2 and then it's times secant squared theta all square root. Now this equals to 2 times absolute value of secant theta. Has to be absolute value because inside this square root always is greater than 0. But secant, if we recall how it is, basically if you have a cos like this, so this is cos theta, secant is just the flip side of it, so it goes up like that. So this is always, well, greater than 0, but it goes less than here. But since our range, we're dealing with only from this point right here, which is negative pi over 2 and pi over 2. So this is always greater than 0, so this just equals to, well, 2 secant theta in our range between here, because this is always greater than 0, so it's always positive. So now we have that right there. So if we just plug everything inside, so square root of x dx over square root, this integral of x dx of x squared plus 4, this equals to, well, x is just 2 tan theta, and then dx, if we scroll back up, that's 2 secant squared d theta. So times it by 2 secant squared theta d theta, all divided by now this one right here. That's just this over here. So 2 secant theta. So 2's cancel. Now the secant at the bottom cancels with the top one. So that equals 2. Take this 2 out. 10. Yeah, 2 times integral of 10 secant theta d theta. And now this, we know the integral of this actually, if you recall from my earlier video, the integral of this is the antiderivative of secant. So this just equals to 2 times it by secant theta plus a constant c. So you can see the video link below for the proof of this integral right there. And so now that we have this, we have to get back to the x variable. So we know that x equals to 2 tan theta, or in other words, tan theta is equal to x over 2, which equals to opposite over adjacent. So that's the definition of tan. So if we look at a right angled triangle, if this is our theta, our opposite is x, adjacent is 2. So the hypotenuse using Pythagoras theorem is just square root of x squared plus 4, or 2 squared. So now that we have that, so to get this secant, well, secant theta is equal to the opposite of, well, basically, yeah, this one's just equal to hypotenuse over this one's adjacent, or the flip side of cosine theta. So that equals to square root x squared plus 4 over 2. So if we plug all this inside, so square root x dx square root x squared plus 4, this just equals 2. This equals to 2 secant theta plus c, which equals 2, this part right here. So the 2's would cancel, so we'll just be left with x squared plus 4 of squared all that plus c. So there is our answer. And as you can see, this is a pretty complicated way. So this is much harder than if we were to do just regular substitution. So if we were to scroll back here, and let's just do a regular substitution right here. So regular integral substitution. Yeah, substitution. So when we do this, notice that this x squared plus 4, if we were to let u is equal to x squared plus 4, then the derivative would basically be du is equal to, well, 2x, and this 4 disappears, dx. So we have covered this top part. So then this basically means, well, x dx equal to du over 2. Just divide this out. So we could already plug everything inside. So we'll get right here, we'll get that the top part's going to be du over 2. Or I'll just write this, yeah, basically 1 over 2 du. And now the bottom is just, well, u square root of u, which equals to, just make it easier, take the 1 over 2 out and make it easier for integration. So this is going to be u to the power of negative 1 over 2 du, and now we can just solve the integral. So this equals 1 over 2, and now if we solve this, you have to add a 1 to it, so that gets to a positive 1 over 2, and now we have to divide by 1 over 2, which is just multiplying by 2. So the derivative of this becomes this, and the 2's would cancel. So we get right here, and then again you have to have a plus c, the constant. So now this equals to, well, u to the power of 1 over 2, the 2's cancel, or just square root u plus c, which equals 2. Plug in this back in, so square root x squared plus 4 plus constant c, and there is our our exact same answer as this one, and we did it much simpler, just very quickly, without a lot of this trig substitution, which is inherently complicated. Anyways, hopefully you'll learn from this video. Like always, you can download these exact notes in the link below, and stay tuned for another math easy solution.